proof unit, okay? If you've heard anything about proofs, I don't know, maybe friends have scared you about proofs. I promise they're not that bad. We're going to see proofs both in this unit and we're going to see it in Unit 4. So we're basically going to be talking about proofs for the rest of the semester. We see it until we go on our Christmas winter break, okay, in December. And then we get back from that, we review for the final. So this will basically take us through the rest of the semester, okay? So this unit in particular is about a month long, okay? We'll have our Unit 3 test November 16th. So you have obviously a lot of time before then, but just as a heads up, this unit is a little bit longer. Okay, and we do have a quiz in between, so all on our unit calendar if you want to look there. Okay, all right. So for today, we're going to be doing an intro to proofs. We're going to be talking about different parts of proofs, how we create proofs, what they look like, all of that good intro stuff. Okay, so it'll be a lot of not a lot of definitions, but some definitions as we go throughout today. Okay. All right, so first thing we're going to talk about is different kind of statements that we can write, okay? So the first is called a conditional statement. And you guys probably have done this in like a science class before, okay? It's where you are writing a logical statement that consists of a hypothesis and a conclusion. So if you guys in science say like, if we mix, I don't know, water with this, then this will happen, okay? So you're testing usually like some type of hypothesis. So we have a hypothesis and we have a conclusion. Okay. And we will write these in if-then form. So it's typically probably how you've seen hypotheses before, and regardless of what class it's been. But the if part's going to be your hypothesis. So if I do this, and your then will be your conclusion. Then I expect this to happen. Okay. We always put the hypothesis first and the conclusion second. We will also be writing converse statements throughout this unit and in our Unit 4. I feel like we see them a little bit more in Unit 4 maybe, but we see them quite a bit still in Unit 3 more towards the end of the unit. Okay, so we do see them quite a bit. And a converse is when you literally just switch the if and the then statements. So the then and if switch places. And we will also be doing things with something called counterexamples, which I feel like you guys do, like if you were to take like a debate class, I don't know if that's still a requirement at the park or not, but if you were to take like a debate class or anything like that, you'll come up with something called a counterexample, which is a specific case where what you're saying is false. So if you're trying to like in a debate class, like prove somebody's wrong, okay, or show evidence that they're wrong or whatever, you would give a counterexample. Okay. All right. So we're going to go ahead and try all of these things now in examples here at the bottom. So in example 1, we're going to start with our first vocab word that we saw, the conditional statement, and we're going to go ahead and write one, okay? So in our conditional statement, we're going to have a hypothesis, we're going to have a conclusion, and we're going to write it in if-then form. So if this is true, then this is also true, okay? So our word that we're going to be writing an if-then statement for is obtuse angles, okay? So let's see here. If I start with if an angle is obtuse, okay, then it should measure between 90 and 180 degrees. Measures between 90 degrees and 180 degrees. Okay. So you'll have to write these. It does also say to underline the hypothesis and to circle the conclusion. So we'll go ahead and do that. So the hypothesis is what's paired with your if. So that would be an angle is obtuse, okay? And your conclusion is what's paired with your then. So that would be measures between 90 and 180. You're supposed to circle one and underline the other. So that's what I did there. Okay. Any questions on how to write an if-then statement? The ones on the homework will be topics that I feel like you guys should know. So I believe it tells you to write if-then for like a midpoint. Okay, you guys should all know what midpoints are. I think I maybe put another type of angle on there. Okay, things that you should know. Okay, so now we're going to move on to coming up with things called counterexamples. So when you read a conditional statement, sometimes it's true, sometimes it's false. So our first step is typically to identify if this thing is true or if it's false. So that's what we're going to start with. And then if something is false, we will write a counterexample. We only write counterexamples if the conditional statement is false, okay? We don't write it if it's true, okay? We don't have to like prove it's true. So for this first statement, it says, if the sum of two numbers is positive, then the two numbers being added are both positive. So my first question to you is, what does it mean if I see the word sum? So I agree that this should be false, okay? Now I need someone to give me an example as to why this is false. As long as your positive number is bigger than your negative, you're going to get something that's still positive. So my counter example to this, the way that I can prove this is false, is by saying -3 plus 4 equals 1, okay? I have a positive sum. I have a positive answer. 1 is positive, okay? But the two numbers that I added together are not both positive, okay? So that's why that was false. And this is a counterexample as to why it's false. You cannot just say, I can add a negative and positive and still get a positive. That is not an example. That's a definition, okay? That is a fact about negatives and positives and all of that. That is not an example. So just be really, really careful with that. On your quiz, it will say, give a counterexample. I can guarantee that's going to be a question on your quiz, okay? And do not just say like a general statement. Make sure you give an example, okay? Those are two different things, okay? Any questions so far? We're going to try another one like this. We don't know yet if it's true or false, but we'll get there. Okay, so this one says, if an angle measures 112 degrees, then it is an obtuse angle, okay? So if something that it could be is obtuse, okay? It can't be any of the other options. So this is actually true. I can't think of any situation where this would be false. Again, because it can't be right, it can't be acute, it can't be straight. Okay. Any questions on why the first one was false or why the second one was true? Now we're going to go ahead for this next example and write the converse of these two statements above.
Okay, my internet cut out and I didn't get mine.
All right, so we're going to go ahead and write the converse of the conditional statements. So for the first one, we started with if the sum of the two numbers is positive, then the two numbers being added is positive, okay? We're going to, for the converse, flip those, okay? So we're going to start with our then statement and make it our if statement, and vice versa. So I'm going to look at what my old then statement was. My old then statement was the two numbers being added are both positive. That is now becoming my if. So if two numbers being added are positive, then, and what used to be your if is now becoming your then. So then the sum is positive. And it's okay if you don't rephrase it like word for word. I'm totally okay with that. Just make sure you're not missing anything super important, obviously. Okay. So if I add two positive numbers together, is there any way that two positive numbers being added could give you something that's negative? Any way where two positives are going to give me a negative. A positive plus a positive is always going to be a positive. That's just what we know. So this statement actually now is true. Okay, keep in mind a couple things. They will not always be opposites. So what I mean by that is just because this started false, that's not why it turned to true when I wrote the converse. Can that happen? Yes, that happens a lot. But does that mean it's always going to happen? No. Sometimes they're both false. Sometimes they're both true. It doesn't always mean they're going to flip-flop. Okay, so just make sure you're not like, oh, well, that was false, so this has to be true. It's not the case. Okay. All right, let's go ahead and try the second one. So we're going to, again, flip-flop the if and the then. So my then was, then it's an obtuse angle. I'm going to start with that now. So if an angle is obtuse, and I'm going to end with my old if. So my old if statement was an angle measures 112 degrees. So then the angle measures 112 degrees. Okay. Now, just because I tell you that it's an obtuse angle, does that mean that if an angle is obtuse, it's always going to be 112 degrees, or could it be something else? It could be 130 degrees, could be 100 degrees. Anything between 90 and 180 qualifies as an obtuse angle. So just because I tell you it's obtuse, it doesn't mean it's always going to be 112. It could be a lot of things. So this one ends up now being false. And a counter example, so a specific example as to why this is false, could be any angle between 90 and 180. So I'm going to give just one answer. Do not put anything between 90 and 180. Make sure you give a specific example. I'm going to say 135 degrees. Okay. Again, this could be any angle measure between 90 and 180. Just pick whatever number you like the best. Okay, I chose 135. All right, so we have two things we're going to define before we actually write our first proof. So the first is what a proof is, okay? So a proof is exactly what it sounds like. We're proving something about a statement, okay, something that we're given. So a proof we call is like a logical argument, okay? So we're going to be putting things like a logical order. We're going to be saying facts that are true. Okay, that makes it logical. So it's a logical argument. Okay, and you probably try to do proofs in, again, like real life situations too. But it shows that a statement is true. So that shows a statement is true. Any questions so far? I'm like trying to look over here and look at the screen at the same time. Okay. So specifically in this class, we're going to be looking at something called a two-column proof. So a two-column proof is exactly what it sounds like. It's literally two columns, okay? And we're going to be numbering our statements and numbering something that we call reasons, okay? So a two-column proof is a type of proof that is written as numbered statement, written as numbered statements. So our statements are, at least for today, going to be parts of an equation. Okay, so we're going to be solving equations today. And we're also going to be having what we call corresponding reasons. So, and corresponding reasons. I'll end it there. The last chunk I think we're good with. Okay. And we are going to have different properties that we are looking at today. Every property that we are seeing today you have already seen in Algebra 1, you probably saw it in 8th grade, you probably saw it in 7th grade, you probably saw it in 6th grade, okay? You have probably been seeing these proofs since you got to middle school, but you probably also didn't call it by these names, okay? Did you solve equations and, say, oh, it's the property of this? Probably not, okay? But we're going to be giving names to these things that we do to solve equations, okay? So the first one that I see here is the addition property of equality. What this tells you to do is if I start with this equation, A equals B, I could add the same thing to both sides and still get something that's true. So I could add, let's say, letter C to both sides, and that would still give me a true statement as long as it's the same. Okay, so what you add on one side, you add to the other side, you're still going to get something that's equal. Okay, same is true for subtraction. So if I start with A equals B and I subtract the same thing from both sides, you're still going to get something that's true. If I multiply the same thing on both sides, you're still going to get something that's true. If you divide by the same thing on both sides, you're still going to get something that's true. And again, you guys have been doing these things for a very long time. We will reference them as we work throughout this problem. So you'll be like, oh yeah, that makes sense, okay. Substitution. So substitution, if I know that A equals B, I can replace A with B and B with A. They can replace each other because they're the same thing, okay? So then you can replace B with A, and again, vice versa, you could replace A with B. Okay. And then for the last one, that's distributive property. Distributive property, again, you guys have already seen, especially you saw it probably a lot last year in Algebra 1. This means that you can distribute the A to both the terms on the inside, and that would give you A times B plus A times C. Okay, none of these should be new properties. Okay, also we're giving names to them now, but none of them should be new. Okay, all right, we're going to use these properties to write our first proof. Okay, so we're going to be writing 2-column proofs. It's literally 2 columns. Okay, it's what it sounds like. So I'm going to start by creating 2 columns. And it tells us for a 2-column proof that you're going to have numbered statements and corresponding reasons. So I'm going to be numbering my statements and my corresponding reasons. The good thing is with proofs is that the format never changes for us. So you're going to always start your problems with a statement side, a reason side. Things are going to be numbered. They're going to look visually the same from problem to problem. Obviously, the problem itself will change, but they should all look fairly similar. Okay. Your first statement is always going to be what you're given. Okay, so we were given the instructions to solve this equation. So your first statement should be the equation that you're given. It's not always going to be an equation, but whatever you're given, that's what's going to go first, okay? And the nice thing with proofs is your first reason, no matter if it's an algebraic proof, a geometry proof, a triangle proof, whatever proof it is that we're doing, your first reason will always be given. There's no other reason why you wrote this, okay? You didn't write it because it's your favorite equation to solve for. You wrote it because you were given that equation to solve, okay? So first reason is always given, and you write what you're given. A really important part with proofs when we do algebraic proofs is that all of your work should not be done in the proof, okay? So I would recommend like a blank sheet of paper, just like scrap paper, or you can do it off to the side. You can do it in your head if you feel confident. Just make sure that you're not showing your work in the proof. A proof is like an instruction manual. So when you like open a manual to like assemble something, you're not given like all of the like work that's done. You're just given the steps to follow. So that's kind of the same idea. Okay, we're just listing the steps to follow. Okay. So I'm going to do mine on a separate sheet of paper. So I'm going to go ahead and just rewrite this equation so I can work with it on my blank sheet of paper. If you show your work in your proof, you will not get full credit. Okay, so make sure you do it separately. Okay. All right, order of operations. Perfect. So we are going to distribute the 3 to both the x and the -5. So that would do this and this. So 3 times x is 3x. 3 times -5 is -15. Everything else should stay the same. After you complete something, so I just completed distributing, that is going to be your next statement. Okay, so statement number 2 is where you end. So I ended with 3x minus 15 minus 2x equals 21 plus 10x. Okay. Now, when I asked you guys what to do first, you told me to distribute. That is your reason. That is what I did to get this second statement. So your reason should be distributive. It's this last one right here. Distributive property of equality. I am 100% okay if you abbreviate property of equality because you see it like a lot. Okay, it's not just going to be today. You'll see it unit 4, unit 3, everything. Okay. You can abbreviate that as just POE for property of equality. I'm 100% okay with that. If you'd rather write it all out, write it all out. Okay. All right. What is my next step in order to solve this for x? The -2, okay, those two should be combined. So that gives you just plain old x. Everything else should stay the same. Once you complete something algebraically, that becomes your next statement. So this is now statement number 3. So we have x minus 15. Okay. Now this reason is actually not listed. We very rarely solve equations with proofs. We do this as an intro because you guys have all solved equations before, but it's not our main focus for the next 2 months, okay? So we're not in algebra, correct? So we don't like give this necessarily like its own like property, okay? But what we did there is exactly what you guys said. We combined like terms, okay? So for reason 3, it's going to be combined like terms. You would only say like addition or subtraction if you're doing it to both sides of the equal sign. We didn't do that here. We just literally took 2 things on the same side and combined them together. Okay, so that's different than like addition or subtraction property of equality. Okay, so just to clarify. Okay, awesome. All right, what is my next step to solve for x? And there's actually a couple answers that you could say here. So when I subtract x from both sides, I have this go away on the left. We're left with just negative 15. And then on the right, we have 21. And 10x minus x is 9x. What you end with after you do something algebraically is your next statement. So this is my next statement, negative 15, 21 plus 9x. And since you guys told me to subtract from both sides, I would write for my reason subtraction property of equality. Just ask yourself what you're doing to solve, and that's literally going to be your reason, okay? So subtraction property of equality. All right, so it looks like we got all the x's to the right. So now I need to get all my constants to the left. How can I do that? Good, we're gonna subtract the 21 from both sides. And I just wanna remind you guys again that there's a couple ways that we could solve this, okay? This is not the only way you could have, done in a different order, okay? But this is the order that we chose, so that's completely fine. So this will go away here. We're left with negative 36 on the left. The 9x stays 9x, okay? When I end, that's my next statement. So negative 36 equals 9x. And to get to that point, you guys told me to subtract the 21 from both sides. So again, I did subtraction, property of equality. Okay. What is my last step? What's my last thing to do to solve for x? We'll divide both sides by the 9. Awesome. So let's see here. Negative 36 divided by 9 is negative 4. And you should have the 9's cancel on this side. Okay. This is my last statement. And I like to put my x first, so I'm just going to put x equals negative 4 instead of negative 4 equals 6. Doesn't make a difference, but this looks a little bit nicer. Okay. And to get that, again, we had to divide. Okay. So my reason is division, property of equality. Will all your proofs be this straightforward? No. Okay. I'm not going to lie to you and say that they're all going to be this nice. But the process will be the same. The setup will be the same. It will mostly not be algebraic, but the setup and how it looks visually will stay the same from problem to problem. So these two last things are just properties that we're going to see really throughout this unit and unit 4 that we'll want to use mainly when we get to our geometric proofs on Monday. You really won't see these in algebraic proofs. There's not really like a need for it, but we'll see it quite a bit throughout unit 3 and a lot in unit 4. Okay. All right, so the first is reflexive. Reflexive, we see more in unit 4 than we do in unit 3. We see it a ton in unit 4. And all this states is that something should equal itself, which I know sounds really silly. It's like saying 3 equals 3, and you're probably like, well, duh. But as we get to triangles and like side lengths and things like that, we'll want to remember this property. So reflexive literally states that something equals itself. Okay, so like A equals A. Okay. If we were talking about a line segment, we would say AB equals AB. It equals itself. If we were talking about an angle, angle N equals angle N. Okay, so whatever you have should equal itself. The way that you're going to see this on the quiz is I'll probably give you something that looks like this. It's like a statement, okay? And I'll ask you what property is being shown. So you would say reflexive, okay, or whatever property it is. Okay. And then we also have something called transitive. Transitive is a little bit trickier because it's not as like obvious, I would say. But it does have a very specific format. So it'll say like, if this is true and this is true, then by default, this is also true. So you'll see like, if this and this, then this. Okay, it'll always be in that kind of format that you'll see. So what this is saying for the first part is that if A equals B and B equals C, by default, A should also equal C. Okay, they should all be equal to each other. So same thing for segments. If I have segment A, B, and C, D, and they're equal, and I have C, D equals EF, then by default, AB should also equal EF. Okay, a good little trick for these is just whatever they have in common, okay, get rid of, basically. And then for any angles A, B, and C, if the measure of angle A equals measure of angle B, and angle B equals angle C, then by default, A should equal